welcome to our journey through the cosmos. Today, we'll explore the incredible story of how our universe came to be, from the Big Bang to the formation of planetary systems. Fasten your seatbelts and prepare to be amazed as we delve into the awe-inspiring story of our universe. Our story begins roughly 13.8 billion years ago, in a moment of unimaginable density and temperature. Imagine a point containing all the energy of the universe compressed into a space smaller than an atom. This is the singularity, the starting point of everything we know. Then, in a blinding flash of light and energy, the Big Bang occurred. As the universe expanded, it cooled, much like air rushing out of a balloon loses heat. This cooling was crucial, as it allowed energy to convert into matter, following Einstein's famous equation, E=mc². In the early universe, this cooling led to the formation of the fundamental building blocks of matter quarks, leptons, and their antimatter counterparts. The Big Bang wasn't just an explosion, it was the birth of our universe, a cosmic seed from which everything we know emerged. In the first fleeting fractions of a second after the Big Bang, something remarkable occurred, a period of exponential expansion known as the inflationary epoch. During this inflationary period, the universe expanded faster than the speed of light, growing from a size smaller than a proton to a grapefruit-sized cosmos in the blink of an eye. This rapid expansion had profound implications for the universe we see today. It smoothed out the distribution of matter and energy, explaining why our universe appears remarkably uniform on the largest scales. Furthermore, inflation amplified tiny quantum fluctuations in the early universe, stretching them to cosmic scales. These fluctuations acted as seeds for the formation of galaxies and galaxy clusters, the large-scale structures that define the universe we observe. As the universe continued to expand and cool after the inflationary epoch, the stage was set for a crucial transition, the formation of particles. This process, governed by Einstein's famous equation, E=mc², led to the creation of fundamental particles like quarks and leptons, the building blocks of all matter. Quarks, the constituents of protons and neutrons, and leptons, which include electrons and neutrinos, emerged from the primordial energy soup. However, the early universe was not just a peaceful assembly line of particle creation. It was a chaotic and energetic environment, filled with collisions and annihilations. The formation of particles marked a crucial step in the evolution of the universe, transitioning from a sea of pure energy to a cosmos populated by the building blocks of matter. Within the first few minutes after the Big Bang, a remarkable event unfolded: the formation of the first atomic nuclei, a process known as Big Bang nucleosynthesis. As the universe cooled to 1 billion degrees Celsius, the strong nuclear force which binds protons and neutrons together became strong enough to overcome the repulsive electromagnetic force between the positively charged protons. This allowed protons and neutrons to fuse, forming the first atomic nuclei. The primary product of this primordial nucleosynthesis was hydrogen, the simplest and most abundant element in the universe, consisting of a single proton. Helium, the second lightest element with 2 protons and 2 neutrons in its nucleus, was also formed in significant quantities. Big Bang nucleosynthesis provides compelling evidence for the Big Bang theory, as the observed abundance of light elements in the universe closely matches the predictions made by this model. After the fiery chaos of the Big Bang and the formation of the first elements, the universe entered a period known as the Dark Ages, a time when the cosmos was shrouded in a dense fog of neutral hydrogen gas. During this era, which lasted for hundreds of millions of years, the universe was opaque to visible light. The newly formed hydrogen atoms were too hot to capture electrons and form neutral atoms, meaning that photons, the particles of light, were constantly scattered by the free electrons, preventing light from traveling freely. Despite the darkness, the seeds of future structures were being sown. Gravity, the architect of the cosmos, began to pull matter together, forming clumps and clusters within the primordial gas. The Dark Ages, though seemingly uneventful, were a crucial period of gestation for the universe. As the universe continued to expand and cool, a pivotal event occurred, marking the end of the Dark Ages and ushering in a new era of light recombination. Around 380,000 years after the Big Bang, the temperature of the universe had cooled enough for electrons to be captured by atomic nuclei, forming neutral atoms. With the formation of neutral atoms, the fog lifted, and the universe became transparent to light. Photons, no longer scattered by free electrons, could now travel unimpeded across vast distances, carrying with them the first light of the universe. This first light, released during recombination, is what we observe today as the cosmic microwave background radiation, a faint afterglow of the Big Bang. Recombination marked a turning point in the evolution of the universe, transitioning from a period of darkness to an era of light. After the universe emerged from its dark ages, gravity began to sculpt the cosmos, pulling matter together into denser and denser regions. These clumps of hydrogen and helium gas, enriched with the remnants of the first stars, became the seeds for the first galaxies. Imagine a universe where vast clouds of gas, swirling and collapsing under their own gravity, ignited into brilliant bursts of star formation. These first stars, massive and short-lived, flooded the universe with intense ultraviolet radiation, ionizing the surrounding gas and shaping the intergalactic medium. As more and more stars formed, they began to cluster together, drawn by their mutual gravitational attraction. The formation of the first stars and galaxies marked a pivotal transition in the history of the cosmos, illuminating the universe and setting the stage for the emergence of more complex structures, including our own Milky Way galaxy. Stars, the building blocks of galaxies, are not static objects but rather dynamic entities that undergo a fascinating life cycle, from birth to death, governed by the interplay between gravity and nuclear fusion. At the heart of a star, gravity compresses matter to incredible densities and temperatures, high enough to initiate nuclear fusion. In this process, lighter elements, like hydrogen, fuse together to form heavier elements, like helium, releasing tremendous amounts of energy in the process. The lifespan of a star depends on its mass, with more massive stars burning brighter and shorter lives. When a star exhausts its hydrogen fuel, it begins to fuse helium into heavier elements like carbon and oxygen. The death of a star can be a spectacular event, ranging from gentle expansion into a red giant to a cataclysmic supernova explosion, scattering newly formed elements into the cosmos, seeding the formation of new stars and planets. Supernovae, the explosive deaths of massive stars, are among the most cataclysmic events in the universe, outshining entire galaxies for a brief period and shaping the interstellar medium with their remnants. As the core collapses, it releases a tremendous amount of energy, blowing off the star's outer layers in a brilliant explosion, a supernova. This explosion, visible across vast cosmic distances, disperses the star's outer layers into the surrounding space, enriching the interstellar medium with heavy elements. Supernovae are the cosmic furnaces where elements heavier than iron are forged. The intense heat and pressure during a supernova explosion allow for rapid neutron capture, creating elements like gold, platinum, and uranium, which are scattered throughout the cosmos. Supernovae, though destructive, play a crucial role in the cosmic cycle of life and death, enriching the universe with heavy elements and triggering the formation of new generations of stars and planets. In the aftermath of a supernova, the remnants of a dead star, enriched with heavy elements, mix with the surrounding interstellar medium, providing the raw materials for the formation of new planetary systems. Within this nebula, gravity begins to draw matter together, forming a rotating disk of gas and dust around a young star, a protostar. As the disk spins, particles collide and stick together, gradually growing larger, forming planetesimals, the building blocks of planets. Over millions of years, these planetesimals continue to accrete material, their gravitational pull attracting more and more gas and dust. The inner regions of the disk, hotter due to the protostar's radiation, favor the formation of rocky planets, while the outer regions, colder and richer in volatile compounds, give rise to gas giants and icy worlds. The formation of planetary systems is a testament to the universe's ability to create complexity and order from chaos, transforming the remnants of dead stars into new worlds, some of which may harbor life. And there you have it, the awe-inspiring journey from the Big Bang to the formation of planetary systems. From an infinitesimal point, our universe has expanded, cooled, and transformed, giving rise to stars, galaxies, planets, and ultimately, life itself. It's a story that fills us with awe and wonder, reminding us of our place in the grand scheme of things. Stay curious and keep exploring the wonders of our universe.